All right, so hash tables, one of the most useful and used data structures. They do not support many operations, which means they're pretty simple to talk about, actually. But the operations they do support, they are amazing at. They basically act like an array with a couple of key differences. All right, so what are the operations that we have for a hash table? We can insert, we can delete, we can look up, and all of those are going to be constant time operations. What are they not good for? They are not good for random access. And they're bad at order. So if you need your items kept in any specific order, they're not very good for that. If you need to access the 10th item, whatever that might be, random access wise, they're not good for that either. But they are good at inserts, deletes, and lookups. So you're guaranteed that those operations will operate in constant time. You're guaranteed you'll get that constant time as long as the hash table is properly implemented and the data is non-pathological. We'll spend more time talking about pathological data in the next set of slides, but for now just know that there are ways to construct a data set that will break this constant time guarantee for pretty much any hash table implementation you can think of. All right, well, let's talk about some examples just to get you an idea of how hash tables can be used. Let's say you want to remove duplicates. You don't want to have more than one of any item. So you're given a stream of objects. You don't want to add an object if it already exists in the hash table. So for example, this would be like detecting distinct visitors to a website. So every time somebody hits a server, you're going to store their IP address in a hash table. And this could also be having a blacklist or whitelist of visitors to your website, or creating an efficient web crawler. You get constant time access to see if something's already in the hash table. How about a second problem for an example? Let's call this the two-sum problem. Let's say you're given an array of integers and a target sum. So, here's A, has a bunch of integers like 16, negative 45, and so on. And you have some target, which could be something like the number 32. What we want to know is, are there any two numbers inside the array that sum to 32? One way to do this, well, let me just pose that as a question here. Think of a naive approach to this. What would be sort of the brute force method for solving this problem? All right, well, a brute force method here would be to add all pairs of numbers. So you're going to take every number and add it to all other numbers and see if that adds to 32. And you're going to try all pairwise numbers, which is going to give you a big O of n squared running time. A slightly better approach, using techniques we've already discussed in class, might be to first sort and then add the numbers. So why are we going to do any sorting? Well, let's say if we take 16, what's the number that you would add to 16 to sum to 32? It would be 16. Well, if our array is sorted, we would just do a binary search for that second number. So let's say the first number, let me take something other than 16, since 16 plus 16 is 32. Let's say the first number is 8. We know that the other number we're searching for is going to be 24. So we would just search the array for the number 24. And the sort here is going to be what dominates our entire running time. And the running time of that is n log n. So this approach is n log n. Slightly better, but not optimal. If we use a hash table, we would do something very similar. We're going to insert all n numbers into a hash table. That's going to take big O of n time. And then we just do a lookup. So for each number in the array, for the 16, for example, we'll see if there's a second 16 in the hash table, which is a second loop through the array, which gives us a total running time of big O of n for using a hash table for this problem. And just to give you some additional ideas of what you might use a hash table for, they're very frequently used as a symbol table in compilers. That was actually the motivating reason for creating hash tables. If you're going through some code and you've got something like x equals 5, and then later on you've got y is equal to something dependent upon x, you want to be able to quickly and efficiently look up this x. So we'll store that in a symbol table, which you can think of as just a hash table for a compiler. They're also very frequently used inside search algorithms. So they help you ensure that you don't repeat the same test. So consider this chessboard configuration. There are many different ways where you can end up at this exact same chessboard configuration. So we can find some way to serialize this chessboard configuration. And when we do that, we can set this chessboard configuration into a hash table and say, okay, we've already been to this configuration and we've already solved for the best move from this configuration. So basically, it's one way to make sure you don't duplicate the same effort.